Any questions?
Can we go over the formulas and just like a quick run through like the formulas and what they're used for?
All right, so the assume the chapter 3 formulas.
Yes.
So I'll do the ones that I know that should be put on there, and then I'll take a quick look just to see if I missed anything. Now, depending on how old your book is, this is, I guess I got this one when the 12th edition first came out. There was a mistake in one of the formulas here. I think it's been corrected in the newer versions of it, and the electronic version better have it corrected. But that first formula should be speed equals distance over time.
On what page?
On page
Yeah,
53.
it is.
The older version says speed plus distance over time. It's a mistake.
What did you say was the correct one?
Should be speed equals distance over time. So Hewitt rates. And preferably, this should be average speed. If I travel from here to Charlotte, it's roughly 100 miles. And I do it in 2 hours. That does not mean I was traveling 50 miles an hour the entire time. So this is an average. If you want to talk about instantaneous speed, well, from a math point of view, you just figure out what is the distance you traveled in a really short amount of time, and then you still do, it's still distance over time, it's just that the amount of time that passes is incredibly small. And has anyone in here had, sorry, I think I might have asked this before, anyone in here had any calculus at all? Okay, good. It's like two.
That's pretty cool.
It's a derivative for those who've had some calculus. Or future calculus students. I would write the same thing slightly differently, because I don't feel like writing out words a lot at the time. So V is equal to the distance over the time. So this is what I would write. Sometimes I might throw in an AVG down here just for average. So let me ask you, how do you know this is speed and not velocity?
There's no vectors involved.
Exactly. Same way you know this is distance and not displacement. So the vector version, the average velocity, is equal to the displacement divided by the time. Try not to block the Noelia the entire time. Oh, okay. His second equation is average speed equals total distance covered over time interval. Let's flash back for a moment. A question before I talk about these two fractions equal to each other. Any questions up to here? All right, so I have two fractions equal to each other. What else has to be true?
C has to equal A and B has to equal B.
No, not necessarily. It could be 1/2 is equal to 2/4.
Oh, they proportionally have to be equal.
Proportionally, yes, okay. What would cross multiplication tell us?
A is equal to B.
Yeah, I think I heard you say it correctly. So when you're cross multiplying, if I have two fractions equal to each other, then multiplying that diagonal, so A times D, has to be equal to B times C. So if I have 1/2 is equal to 4/8, well, 2 times 4 is equal to 1 times 8. Unless the math people have been lying. So the another equation that Hewitt presents is basically just a similar to this one. Now, if I look at this right here, I've got a fraction on my right-hand side, or right-hand side, or right-hand side. On the left-hand side, it doesn't look like a fraction, but I can always turn anything into a fraction by putting it over 1. So if I take v is equal to distance, or speed is distance over time, I can stick that over 1. And so now v times delta t, speed times time, must be equal to distance times 1, which is just distance. Except he writes it out. Distance is equal to speed times, he then says average speed at this point, times time. And if you think of this, it's an equation, but you can also just think of it as a sentence in math terms, and so he takes that route and capitalizes the D. And he seems to capitalize the first word of each of those equations that he writes out. Anyway, so those are the equations that are in the plug and chug section. There are no equations in the summary section, so you're guaranteed at least those equations right there. Questions up to here before I take a look at what other equations I also put on here. Okay. I also threw in the distance fallen and free fall, which he writes as b equals 1/2 gt squared. That's if I take an object starting at rest and I let go, how far does it fall in a certain amount of time? And then the other one of how fast is it going is v is equal to gt. Looks like I got a couple more equations than what he has in that section right there. So this is how far does it fall, as I mentioned before. If I know the acceleration due to gravity and the time it takes to fall, I can figure out the distance. Or how fast is it going if it starts at rest, is the speed is equal to g times t. If it doesn't start at rest, then my change in velocity is equal to gt. Technically, it could be positive or negative, so let's make it a vector. I wonder why those equations are not in there. Is this what you were wondering when you wanted me to go over the equations? Okay. We also have acceleration. All right, so the shorthand, acceleration is the change in velocity over the change in time. Again, I can make it a fraction here. So I have acceleration times the change in time is equal to delta v times 1. Which is what I have similar over there. The difference between this equation and that equation is this is a free fall problem because g is the acceleration due to gravity, and this is general for any value of acceleration or the average acceleration. And I believe he writes, yep. So he writes this out in words, and that's what I have at the top of the page. That acceleration is equal to, what's the wording he used? Right, it's just change in velocity. Change in velocity over, I think he says time interval. Yeah, time interval.
What is the difference between acceleration and change in velocity?
They go hand in hand, because that's the only vector I have on the left side, and this is the change in velocity is the vector I have on the right side. They have to be in the same direction. But the difference is the time factor. So if I go from 20 meters per second to 30 meters per second in 5 seconds, my change in velocity is 10 meters per second.
Okay.
So change in velocity. Final minus initial. So 30 minus 20, 10 meters per second. My acceleration is going to be whatever that change is divided by the amount of time it took to do it.
Okay.
So that would be 10 divided by 5. So my acceleration, 2 meters per second or meters per second squared.
Cool beans. Thank you.
Can I just ask you a question? With this written out like this, how do you know that this acceleration is a vector?
Because you use velocity on the other side.
Yeah, I really wish they had come up with a different word, but acceleration can be a scalar or a vector, which I suspect was one of the master set 3 questions. So on a quiz or test, I'm not saying that I haven't had a lapse somewhere in there, but I tried if I'm asking for acceleration, I try to give you, acceleration, comma, and then I'll put either A with a vector symbol over it or A without, just so you know which one I'm talking about. Physics textbooks like to just use the word acceleration, and you're supposed to know it from context, which one they want.
How do you calculate acceleration? Like, that's a scalar quantity, acceleration.
How do you calculate acceleration? Change in velocity over how much time it took. There's an example right there.
No, but if it's scalar, not vector.
Oh, that's change in speed.
Okay.
So this would come up with the same answer. Here's an example where it's not the same answer. I go from 20 meters per second to negative 20 meters per second in 10 seconds. My vector acceleration is my change in velocity, so that's negative 20 minus 20 divided by the time. So that's negative 40 over 10, or negative 4 meters per second squared.
And would scalar acceleration just be 4 meters per second squared?
No, it's not that simple. I gave a more complex one than I probably should have. If it goes down to 0, in other words, we're not having some on the plus side and some on the minus side, so this would be initial velocity, final velocity. So as long as I'm saying on one side of it, then that's still suddenly thinking of the exceptions. So the way you would have to solve this with the 20 and negative 20 is you have to sort of treat it as 2 bits. I'm going from 20 to 0, and then 0 to negative 20. Or from a speed point of view, since the scalar acceleration deals with change in speed, so I go from 20 to 0 in, we'll just say 5 seconds, and then 0 to negative 20, or if it's speed, positive 20 in 5 seconds. So my average acceleration for the first part is still gonna come out to 4. Something's messed up there. That's a bad example. Scalar acceleration. I deal with the scalar acceleration so rarely.
Is it not gonna be asked for on our quiz or anything?
I don't think there's any scalar acceleration there.
Will it be asked on, for a master set?
I think I do, I think primarily hang out in the vector. Was there a master set question that dealt with scalar acceleration?
I think there might have been, or maybe I just didn't understand it right. Let me see.
An example where scalar and vector acceleration are different. This is the thing that kept popping into my head, and I was trying to avoid it because it's a chapter 8 thing. If I'm traveling around in a circle at a constant speed, so if I'm taking the curve at 50 meters per second, if you have good tires and it's a dry road, over 100 miles an hour. If you're taking a curve at 50 meters per second, your velocity changes because your direction goes from that direction to that direction. Your direction changes, therefore your velocity changes, therefore you do have vector acceleration. However, your speed doesn't change at all. So here, your scalar acceleration would be 0 meters per second squared. And your vector acceleration, as we will get to, will be 50 squared divided by whatever the radius of curvature of the curve is. Or R. I just introduced some stuff. It's sort of a sneak preview. Kind of like at the end of Marvel movies when they have that one scene at the very end. This is as exciting. I've seen enough of the Marvel movies to go, yeah, that is about as exciting as those movies are. No movie should have more graphic designers and stuff in it. Other question? Oh. I also have acceleration along a straight line in one direction, so just one way. Change the speed over the time interval. I think we've covered that one already. Instantaneous speed equals acceleration times time. Again, that's going in one direction. I think those are the equations. Other questions from chapter 3? Brianna?
I know you went over the ball thing at one point, but I didn't put it in my notes. Could you go over that again? It's 44. Because I don't understand the answers either.
If I take two objects of different weights, and I let go, which one will hit the ground first?
They won't. The same time.
All right. Because their velocity will change at the same rate. They both start at 0, and they both, since they're matching each other speed for speed or velocity for velocity, they'll both hit the ground at the same time. So from that, the answer to part B is that the acceleration is always the same. The rationale for that, there's a math rationale which some students appreciate, and then there's the non-math one that other students appreciate. From chapter 4, you'll see that the total force on an object is equal to mass times acceleration. So therefore, my acceleration is equal to the total force divided by the mass, which I think is closer to the way that Newton expressed it, except in Latin. If I'm dropping an object, what force is acting on it while it's falling?
Gravity.
I'm gonna nitpick that.
Its weight?
Yes, thank you. What's wrong with just saying gravity?
Because the weight is also a factor in the gravity,
What else is a factor in gravity?
where you're.
Where you're at.
Okay, so that would affect other things, yes. I was thinking, one of the things that's triggering in me is I was grading the master set 2, and a number of people put down for the object that was thrown in the air that the force acting on it was gravity. Gravity is not the name of the force. I know it's often used that way, but it's not the name of the force. The force is either the force due to gravity, or if you're close to the surface of a planet or moon, weight. Either one of those will work. There's also acceleration due to gravity. There's a gravitational constant. Those are the big 3 things that I have found too many students will call them all gravity, and they are very different. And then there's curvature of space and time because of gravity and things like that. There are many aspects to gravity other than just the force. All right, so if I have weight acting on it as it's falling, what's the formula for weight?
9.8, oh.
That's acceleration due to, I think, assume you were going for. Formula for weight. And there's an example right there of gravity meaning something completely different than what was mentioned before. Be more specific? Yes. So if that's the force, if the only force acting on it is the force due to gravity, and I plug that in here, then my force is mg, and then I divide by m. M cancels out, all I'm left with is my acceleration due to gravity. That's the math explanation. The non-math explanation, I take these 2 markers, which have roughly the same mass, although that part's somewhat irrelevant. If I drop them side by side, they will fall at the same rate. If I connect it, that doesn't change anything. It's, even though I've now made my object twice as massive, that does not affect how fast the thing actually falls. It's just they're still falling side by side. There's just some flimsy little connection right there. So that's sort of the